So to start the binomial theorem, we're going to start with something called Pascal's triangle. And Pascal's triangle is shown to you over here. This is just a few rows of Pascal's triangle, but it would continue sort of infinitely. Pascal's triangle was named after a man named Louis Pascal. And he was a French mathematician, philosopher, and he came up with this triangle. And the way that the triangle works, if you haven't noticed, is, well, let's start with sort of the diagonals. What do you notice about that? They're all one, yeah. So along the diagonals or along the ends of each row, those are 1. So it starts with a 1 at the top, and then the next two are 1, and then the end numbers on the next row are also 1. And then what about the middle numbers? There's addition. Yeah, so like the first two rows you kind of have to be given. Then you go down here and you get 1, right? So these go down this way. How do you think we would get the 2? Yeah, add the 2 numbers that come above, right? If you want to get the 3, you do 1 plus 2. The next 3 is 2 plus 1. Okay, this guy is 1 plus 3. 3 plus 3 is 6. 3 plus 1 is 4, etc. Okay, so all other numbers in the rows are the sum of the 2 numbers above. Okay, so let's actually, just so we can get a sense of this, write out the next row. So when you're writing out the next row, the first thing you want to do is make sure to extend the 1s. Okay, so what would the next number be? 8, yeah, and it kind of goes in the middle of the 2, like a pyramid, it's staggered. And then the next one? 28, 30, 56, yeah, 70, oh, 70, sorry. And then 56 again, 28, and 8, okay? And the other thing to notice about the Pascal's triangle is that each row is like a palindrome. You can read the numbers from left to right or right to left, and they're in the same order. Okay? So what I would like to do now is just sort of also pay attention to some other patterns that we might see. So I'm going to kind of make some horizontal lines here so that we can kind of look at patterns within each row as well. And chart this out a little bit. Okay, so this first row is row 1. Oh, whoops, I wanted to do that. Oh, it's not letting me pick blue. Let's see. Nope. I can't do blue anymore for whatever reason. Let's see if I can do it this way. Nope. I guess we're going to be red from now on for the rest of class. Okay. Why does the smart board do weird things to me? I don't know. Okay, so row 1, 2, 3, 4, 5, 6, 7, 8. This would be the 9th row. Okay? And the other thing that I want to look at is the sum of the numbers in each row. So in the first row, there's only one number. That would be 1. What about the second row? 2. Third row? 4. 8, yeah. Next? 16, yeah. So can you guys see a pattern here as well? What would the next one be? 32, 64, 128, 256. Okay, and these happen to be powers of 2. So if you think of the row number as n, the nth row, 1 is 2 to the 0, 2 to the 1, 2 squared, 2 cubed, 2 to the 4, 2 to the 5, 2 to the 6, 2 to the 7, 2 to the 8. Okay, so what's sort of the connection between the row number and the exponent on 2? It's, yeah, so the exponent is n minus 1, right? The base is 2. The exponent is n minus 1. Okay, now we actually saw these numbers come up on Monday in a problem that we did with permutations, which was a pathway problem. And I told you at that point that we were actually going to come back to those problems a little bit later on. And we're going to do that now because when you do a pathway problem, the numbers that show up on the grid are numbers within Pascal's triangle. Because to get the number of paths, for example, to this intersection point, add the number of paths from the other two intersection points that lead to that one, which is a similar type of rule that you can do in Pascal's, that follows Pascal's triangle. The other way that we did this question, I just want to see if this makes a difference. Because I really don't want to be in red for the rest of, nope, I guess I'm just going to do red. Okay, so one way that we looked at this was by actually drawing the number of paths on the grid. Okay, and you can work all of these questions out. You can do it on a grid. You can think of this as a permutation question where you are arranging, in this case, you have to go right and down. And you're going 4 blocks right, if you want to think about it as blocks, and 8 blocks down. And so that's 8 objects, right? So as a perm, you're arranging 8 objects. But some of them are identical, right? So there's down, 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 and right, 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 right. Okay, and so the way that we figure out the number of permutations when some of the objects are identical is we start with what if they weren't identical? If they weren't identical, there would be 8 factorial ways of arranging 8 objects, but then we have to divide out the number of ways that you could arrange each of the identical objects if they weren't identical. So that would be 4 factorial times 4 factorial. Okay, so as a permutation, you can think of this problem this way. And now we can actually add the third way of seeing this, which is thinking of it as a combination in which you have to choose. You can either think of it as down 4 times, or you have to choose right 4 times. But once you choose down 4 times, the right 4 times will fall into place, because that's the other direction that you can go, or vice versa. Once you choose right 4 times, the down 4 times will fall into place. So you can think of this also as 8 choose 4. And the 4 would either be 4 down or 4 right. Once you choose those, it goes into place. And the reason why this works is that you have to go down 4 and right 4. It doesn't actually matter what order you go down 4 in and what order you go right 4 in. You can go down and right 4 in any order, and you end up still at point B. Okay? Now 8 choose 4 is 8 factorial over 4 factorial times 8 minus 4 factorial, which is exactly what we see there. Okay, so now we have sort of 3 ways of understanding these pathway problems. So now we're going to up the complexity a little bit. Okay? So here's just another example. In this case, if you're going from A to B, you're going down 2 and right 4. So there's two ways of thinking about we have the grid, so that's one way. If you want to think about it in terms of a permutation, you have to go 1, 2, 3, 4, 5, 6 blocks. But 2 of them are identical and 4 of them are identical. So 2 factorial, 4 factorial, right? Or as a combination, you can think of having to choose, you only really have to choose one direction. Because once you choose those one direction, the remainder of the blocks fall into place, because that's the only other way that you can go. So you can think of it as 6 choose 2, which is, say you're choosing where the downs are going to go, or 6 choose 4. And these are actually equivalent to one another, right? This one is 6 factorial over 2 factorial times 6 minus 2 factorial, which is 6 factorial over 2 factorial times 4 factorial. And this one, this would be, you're now choosing the rights instead of the downs, would be 6 factorial over 4 factorial times 6 minus 4 factorial. So no matter how you slice it, you end up with that 4 factorial times 2 factorial in the denominator. Okay, it ends up being the same value. Okay, so now what we're going to do is look at some more complex pathway problems, which is what if you have several grids that are sort of put together on the corners, and then you wanted to know how many ways do you have to go from A to B. Now, in this case, if you add this point in here, the only way to get from A to B if you're going right and down is you have to go through that point, right? You've got to go through C. Okay, so if we were to actually write the numbers along the sides of the grids, right? If we're going, let's say, from A to C first, okay? Going down and right all along the left side and the top would be one way to get to each intersection. So there's one way to get here, 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay? To here, there's 2 ways, and then 3 ways, and then 4. So I'm just adding these two, 5, 6. This is 3, 6, 10, 15, 21. 4, 10, 20, 35, 56. You can see the numbers start to get quite large quite fast. This guy would be 5, 15, 35, 70, and 70 plus 56 is 126. Okay, and then here, the last one, 6, 21, 56, 126. So that's, here would be 252. Okay? Now, once you get to C, I'm not actually going to fill out this entire grid because what you'll see is the numbers get very large. But once you get to C, if you think about, there's 256 ways to get to here. How many ways are there to get to there? If we're going here, how many ways are there to get to that point? There's one way from C, but there's 252 from here. So if we want to go here and here, it's 252 times 1. So all of these along the end of that second rectangle or second grid are 252, going in both directions. And same here. Okay, now at this point, I mean, we could do the next one, The next one would be 504. It's really impractical to keep filling this out on the grid because the numbers are getting so large. And particularly when the numbers get large, it is hard to keep track of them. Yes?
How would, like, say 3 down, how would that be 252? Because if it takes 252 ways to get to point C and then you move 3 down, it could be like 250.
There's only one way to go 3 down though. So if you start here and you wanted to go here, let's say, there's one way to do it. But you have to go through here and there's 252 ways to get to there. Therefore, there's 252 ways, if you're starting at A, to go 3 down to here, right? So the numbers get very, very, very large very quickly. And so really at this point, the more efficient and usually more accurate way, because people usually make mistakes in these grids, to do this is to treat it either as a permutation with identical objects or a combination. So if we were thinking about the first one, for example, as 10 blocks in total, and we have to choose 5 in one direction, 5 right or 5 down, the number of ways to get from A to C would be 10 choose 5. Okay. The number of ways to get from C to B is 1, 2, 3, 4, 5, 1, 2, 3. So that's 8 blocks in total. And then you either have to choose the 3 right or the 5 down, but we've seen from the previous example that you're going to get the same value no matter what. So just choose one of them, choose one direction. And if we multiply these two together, because we have to do this and this, the total will be 10 choose 5 times 8 choose 5, or this could be a 3. Okay? And that's a large number. 10 choose 5 is 252? Should be, because we did it on the grid. I hope it's 252. Actually, the TI is, or not the TI, the Casio is way easier to do these problems on because the menu with all those buttons just, I'm so impatient with these things opening. Okay, here's the TI. Let's do the Casio. Okay. So on here, there we go. So I'm going to go 10 choose 5, 252, and 8 choose 5 is 56. And just for good measure, let's do 8 choose 3 as well to show that it doesn't matter. It's also 56. So this works out to be 252 times 56, which is, I don't know, in the thousands. Something like 13,000, I'm guessing. 56 times 252. 14,112. Okay, now you don't want to have to be drawing 5-digit numbers on the grid, right? Because you'll start to lose track of them, and it's just, I mean, some people have the talent of being able to write really, really tiny, and if you can do that, I can't, but if you can, go for it. But yeah, the numbers get large quite quickly, particularly when you're working with more than one grid. Okay? If we were to do this one, right? If you think about the first grid, let's say we're going A to C, C to D, D to B. From A to C, we've got to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, 14, 11, 12, 13, 14 blocks. So A to C would be 14, choose, you can either choose 3 or choose 11. Doesn't matter. Going from C to D, we have to go 1, 2, 3, 4, 5 blocks. So this would be 5, choose 3 as well, because you're going 3 down, or 5, choose 2. Doesn't matter. And then going from D to B, we have to go 1, 2, 3, 4, 5, 6, 7, 8 blocks. So this is like 8, choose 2, let's say, if we keep down direction consistent. Okay, so the total will be 14, choose 3, times 5, choose 3, times 8, choose 2. And that gets to be a very, very, very large number. 14, choose 3, times 5, choose 3, times 8, choose 2. Okay, so that's 101,920 ways. Yes? Oh, yeah, sure. The reason why I'm doing it on the Casio is because getting to this button on the TI is a pain in the butt. So let's say I just wanted to do 14, choose 3. I would go 14, and then you have to hit the math button and go over to the right to probability. And then it's number 3, choose 3. And then times 5, choose 3, so times 5. Oh, wait, sorry. On this one, I have to do this first. Put it back up there. Times 5, and then hit that math button all over again. Go over to probability, choose 3. Go back up here, times 8. Math, probability, 3, 2. There we go. Okay. If you do have a Casio, this is one of the other features where it's easier to use the Casio because you don't have to go through that menu every time. And when I marked a combinations question on the 30-2 diploma, and I happened to bring both calculators with me, and everyone else at my table was really jealous because the TI is painful if you have to. Because when you mark a diploma, if someone makes a wrong answer, you got to figure out why they're wrong and how much they're wrong by. Takes a lot. You got to do a lot of calculator work. Okay. So let's talk about the binomial theorem and how this all relates to Pythagorean, or sorry, to Pascal's triangle, both P. Pascal's triangle. Okay? All right, so firstly, what is an example of a binomial? X plus 3. Sure, it's a polynomial with 2 terms. Okay? A binomial with 2 terms. Okay? So the binomial theorem helps us to expand powers of a binomial. So what I mean by that is, let's say we have a plus b to the 21. Okay, a plus b is a binomial. We're now raising that to the power 21. Now, if you were to expand that the same way that we've expanded polynomials before, where you start with 2, you multiply them out, then you bring in the third, then you bring, like that would take forever. It would be painful. And probably somewhere along the way, you would make a mistake. Okay, so what we're going to do is start to look at a few powers of a plus b and see if we can notice some sort of pattern. Okay, so let's start with this. A plus b to the 0. Okay, what is a plus b to the 0 equal to? 1. Okay, what about a plus b to the 1? Yeah, and what I'm going to do, actually, is what I really want you to pay attention to, because all of the terms in the expansion after the exponent of 0 are going to have a's or b's in them, or maybe powers of both, like an a cubed times a b squared, something like that. Okay? So what I want you to pay attention to is the coefficients. Okay? What about if we did a plus b squared? Yeah, so some of you guys just know what it is, right? But it's a squared plus ab plus another ab plus 2ab plus b squared. So this is 1a squared plus 2ab plus 1b squared. Oh, okay. Now let's say we do a plus b cubed. Okay, well, a plus b cubed, we can take a plus b squared and multiply it by another a plus b. We're just bringing in another factor of a plus b. Right, so that's a cubed. I feel like I'm in the way. Let me do it that way. Plus 2a squared b plus ab squared. Right? Then plus ba squared plus 2ab squared plus b cubed. Now when you simplify this, we have some like terms here. Right? So we've got the a cubed, and then this term and this term are the same. A squared b and b a squared are the same. So that's all together we have 3 of them. And then same thing here. We've got this guy and this guy. Those are the same terms. So we have 3 of those. And then plus b cubed. So if we write out this expansion, we have 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. Okay, so what do you guys notice? Yeah, the coefficients are the numbers that show up in Pascal's triangle. Okay? Okay, so let's actually try and figure out, what do you think a plus b to the 4 would be? What do you think the first term would be? 1a to the 4. Okay, what's the next coefficient going to be? 4. Okay, now what is happening with the powers of a and b as you move from left to right? Yeah, so the a's are going down by 1. The b's are going up by 1, right? So this next one would be a cubed b to the 1. And the next one? 6. A squared b squared. The next one, right? So 3 and 3 is 6. 3 and 1 is 4. AB cubed. This goes down by 1. That goes up by 1. And then plus 1 b to the 4. Okay, and this is true. The coefficients in this expansion are numbers that appear in Pascal's triangle. Okay, now not only that, okay, you have this over here. I just didn't show it to you. But the numbers that appear in Pascal's triangle are various combinations. So if you look at the number 1 that is equivalent to 0, choose 0, because 0, choose 0 is 0 factorial over 0 factorial times 0 minus 0 factorial. And we spoke about this yesterday. 0 factorial is equal to 1. So this guy's equal to 1. Okay. 1 choose 0 is 1 factorial over 1 factorial times 0 factorial, which is also 1. This one is also going to be 1. This guy, 2 choose 0. And I'm not going to do all of these. I'm just going to do a few examples. Right? If you do 2 choose 0, it's 2 factorial over 0 factorial times 2 minus 0 factorial, which is essentially 2 factorial over 1 times 2 factorial. 2 factorial over itself is equal to 1. Okay? And so if we take maybe one of the middle numbers, let's say we take this guy, 5 choose 2. Okay, just to test it out. 5 choose 2 is 5 factorial over 2 factorial times 5 minus 2 is 3 factorial. Right? Now 5 factorial over 2 factorial times 3 factorial is 5 times 4 times 3 times 2 times 1 over 2 times 1 times 3 times 2 times 1. So these pieces cancel. You're left with 5 times 4, which is 20, over 2 times 1 is 2. 20 over 2 is 10. Okay? Now, this is really powerful because up to this point, to figure out various numbers within Pascal's triangle, you had to start at 1 and draw the entire thing. And the only way that we could get those numbers is by adding the 2 that came before. But now we can see that actually all of the numbers that appear in Pascal's triangle are combinations. And so now we can actually say, well, what if we just wanted like the 4th number in the 14th row? How would we figure that out? And we have a way of doing it with combinations where we don't actually have to start at 1 and go all the way down 14 rows. Okay? So what we are sort of going to be doing with this is we are going to be learning essentially how to use, this is called the binomial theorem, which involves Pascal's triangle and combinations, to figure out the expansion of something like a plus b to the 21. Or we may also just want one term in that. Like, what if you wanted the 6th term in a plus b to the power 21? What would that be? And this is all called the binomial theorem. Okay? So what I'm trying to decide what to do is, I think perhaps we should maybe leave it here and pick up with the rest of this tomorrow, and just see like how do we actually use all of this, because we only have 25 minutes left and I know we're going to run out of time. And so I think I'd like to just leave it here, lay this groundwork, and then we'll see how we can apply this all tomorrow. Just so you know, and the other reason why I want to leave it here is because obviously something happened when I converted this to a PDF, and I don't know what it is. I have to look up what those numbers are in my Word doc. So this is a good place to stop.